A quark-gluon plasma, or quark soup, is a phase of quantum chromodynamics which exists at extremely high temperatures and/or density. This phase consists of almost free quarks and gluons, which are the basic building blocks of matter. Experiments at CERN's superproton synchrotron first tried to create the quark-gluon plasma in the 1980s and 1990s. The results led CERN to announce indirect evidence for a new state of matter in 2000. Current experiments at Brookhaven National Laboratory are continuing this effort. Although the results have yet to be independently verified, scientists at Brookhaven have tentatively claimed to have created a quark-gluon plasma with an approximate temperature of 4 trillion degrees Celsius. The quark-gluon plasma contains quarks and gluons, just as normal baronic matter does. The difference between these two phases of quantum chromodynamics is that in normal matter, each quark either pairs up with an antiquark to form a meson, or joins with two other quarks to form a baron, such as the proton and the neutron. In the quark-gluon plasma, by contrast, these mesons and barons lose their identities and dissolve into a fluid of quarks and gluons. In normal matter, quarks are confined. In the quark-gluon plasma, quarks are deconfined. A plasma is matter in which charges are screened due to the presence of other mobile charges. For example, Coulomb's law is modified to yield a distance-dependent charge. In a quark-gluon plasma, the colored charge of the quarks and gluons is screened. The quark-gluon plasma has other analogies with a normal plasma. There are also dissimilarities because the colored charge is non-abelian, whereas the electric charge is abelian. Outside a finite volume of quark-gluon plasma, the color electric field is not screened, so that the volume of quark-gluon plasma must still be color neutral. It will therefore, like a nucleus, have integer electric charge. One consequence of this difference is that the color charge is too large for the perturbative computations, which are the mainstay of quantum electrodynamics. As a result, the main theoretical tools to explore the theory of quark-gluon plasma is lattice gauge theory. The quark-gluon plasma can be created by heating matter up to a temperature of 2 times 10 to the 12th Kelvin, which amounts to 175 million electrovolts per particle. This can be accomplished by colliding two large nuclei at high energy. Lead and gold nuclei have been used for such collisions. The nuclei are accelerated to ultra-relativistic speeds and slammed into each other while Lorentz contracted. They largely pass through each other, but resulting hot volume called a fireball is created after the collision. Once created, this fireball is expected to expand under its own pressure and cool while expanding,